Back in 2020, I started a video series all about gravity, the history of it, whether or not it's a force, and how Albert Einstein discovered general relativity. And at the outro of my last video, I said, okay, now we can quantify the curvature of space-time. Now what? Now what is a lot of math. That's why it took me a couple of years before actually coming up with this video, because it was a lot of math that I had to digest first, and I just didn't have the mental capacity for this on top of doing university academic work. So yeah, I make these videos as a way to relax from school. Usually I do more school in a different form, but yeah, so that part was a little too intense for me back then, but right now it's a little better, yeah. So in the next few minutes I will talk about what's going on with matter and energy and how it's related to space-time curvature. And then immediately after this, I'm going to talk about the physical quantities that we're trying to measure from outer space and how this is related to space-time curvature, something that is really abstract to us. I don't know how to make a fucking YouTube intro, but yeah, hi, my name is Beam and I'm gonna teach you some science. First, we start with two massive objects in a place far, far away. Because if they were near, the thing is we would probably die. So these massive objects need to be as massive as black holes, for example, so we can get a significant amount of gravitational waves. So we want them to be pretty far. Now these objects have their own properties. Mass, of course, and this is related to the space-time curvature like so. Those tiny letters at the bottom we'll talk about later. This left side with T tells us about the matter and energy present in a region of space-time. Most of the time, this is what we're after. On the right side, you have a huge S constant, which just means it's a really big value. And then you have this big letter G over here. This G tells us about the curvature of space-time. The left side is what we're after, and the right side is what we get to measure essentially. To know how much matter and energy there is in some region of space-time, for example, in a place that is far, far away, so we can't physically weigh them, we can't just put them on a scale. To know this amount of matter and energy, we can start with space-time curvature. We measure space-time curvature, so how the fuck do you do that? Like, this is space-time. You want it to fucking curve. We'll find out. We start with a metric, which sounds like a wild term, but what this is just a shorthand to see how distances between things change, depending on space-time. That's all it is. Usually, distances between things don't change unless we move them. So there's a rolled mat behind me, and then there's this chair I'm sitting on. The distance between these two objects, they won't change unless I move the chair, I move the mat, I stand up and get the mat. So sure, that's fine. That's normal life. You know, it's something that is standing just right there. It shouldn't be moving. But this video wouldn't really be here if the story ended there. There is one way we can make the distance between that mat behind me and the chair I'm sitting on change. And that's by passing a gravitational wave between these two objects. To be more concrete, let's define this metric that we started talking about mathematically. Our metric would look like this. Once again, it's those tiny letters at the bottom, and the idea is the same with our first equation. We have 4 dimensions including time, and for each of those dimensions, there's a specific value of change. The relationships are still the same, so it's fine to just look at these equations without thinking of those matrices or those tiny letters. We don't really care about the specific values. What I want to show you is the relationship between these equations that you would usually be bombarded with if you looked up gravitational waves. This term right here tells us about a region in space-time that is flat, without any curvature, as if there's no matter and no energy in this region. We can disturb this flatness by passing a gravitational wave. And this term here represents that disturbance. More physically speaking, these disturbances are interpreted as a quantity called strain. You may have heard of stress and strain in your physics classes in high school, and it's the same strain in this case. But instead of strain in a piece of metal, for example, we're talking about strain in space-time. We were talking about gravitational waves causing a disturbance in our metric equation. How come now we're talking about strain? A gravitational wave would affect space-time in such a way that once this wave passes through the space between two objects of a fixed distance, this distance could get larger or smaller. To better compare changes in the distance from different experimental setups, for example, we divide it by the original distance to obtain that quantity, the strain. With these values for strain, we use a connection known as a Christoffel connection. What this just means is that the trajectories for any object in the universe can be obtained. I'm not going into the math of these Christoffel connections for now. What we want to understand right now is the flow from equation to equation, quantity to quantity. Eventually, we obtain a Riemman curvature tensor and then compress this into a Ricci tensor. Lastly, we should obtain a Ricci scalar. This single value tells us about the curvature of the spacetime we have been inspecting, and voila, we're pretty much at the finish line. The main idea is this: for a significantly large object out there in the universe, we may be able to detect some gravitational waves from this object and use those waves to understand the mass, for example, in this region of space-time. And it's even better when it's two massive objects interacting. So two black holes merging, for example, is one of the many examples that you see in gravitational wave studies. It's some region out there containing two black holes merging, and this kind of interaction, it produces a ripple in space-time that passes through huge ass distances and reaches us. To understand more of the Big Bang, for example, and especially at that point where the universe was opaque, light wouldn't be able to pass through, and we can't really rely on electromagnetic radiation to tell us about what's going on at this point during the Big Bang. We can turn to gravitational waves. For such a long time, we've been observing and studying the universe with just electromagnetic radiation, and now we're paving the way for using gravitational waves, gravitational radiation, to understand the universe. From way long time ago of not knowing what the universe is made of, or if space-time is something like Newton curve. How did we end up here with so many tools, so many equations to refer to understand the universe? Watch these videos. And this gravitational wave story is not done. I feel like it deserves its own video because it's about using rotating massive objects in outer space as our own clock. So that's pretty wild. So I think it deserves its own video. These objects regularly emit radiation as they rotate, and the pulse that we observe here on Earth from these rotations, well, they should be regular as well, so they're kind of like clocks, unless a gravitational wave passes by and fucks all of that regularity up in a cool way, of course. So that's what we're going to talk about next time. Thank you for watching this video. I hope you learned something about gravitational waves, and I'll see you next time.